Let's discuss a topic called nuclear spin. Nuclear spin is nothing but the total angular momentum of a nucleus. We know that for an electron, there is orbital angular momentum and spin angular momentum, and the total angular momentum is a resultant of both these. Now, if you are considering a nucleus contains protons as well as neutrons. Both are spin half particles like the electron. Protons as well as neutrons both have orbital as well as spin angular momentum. So the total angular momentum of the nucleus would be coming from the resultant orbital angular momenta of all its constituent particles and resultant spin angular momenta of all its constituent particles. The resultant of both these quantities would give me my nuclear spin or the total angular momentum of the nucleus. Usually, to avoid some sort of confusion, we always give the total angular momentum of the nucleus or nuclear spin with the letter I, capital letter I. So don't confuse nuclear spin uh, as coming from the spin angular momenta alone. It's not like that. Nuclear spin is just another term for the total angular momentum of a nucleus, and it is coming from the resultant of orbital angular momenta as well as spin angular momenta of all its constituent particles. Now, what are the different values that nuclear spin can take? Nuclear spin can take integral values like 0, 1, 2, 3, etc. And it can also take half integral values like half, 3 by 2, 5 by 2, etc. Nuclear spin obeys the quantization rule as obeyed by electron angular momentum. We have already come across the quantization rules satisfied by the orbital as well as spin and total angular momenta of an electron when we learned atomic spectroscopy. So nuclear spin also satisfies such a quantization rule where magnitude of angular momenta of nucleus is given by root of I into I plus 1 h cross, where I can take any of these values. This is the magnitude of total angular momentum of a nucleus. So let's see what is the magnitude when I equal to half. When I equal to half, the magnitude happens to be root 3 by 2 h cross. Just plug it the value I equal to half here in this relation. Now when I equal to 2, magnitude is root 6 h cross. Okay. Now let's see the angular momentum quantization condition. We know that for an electron, the orbital angular momenta satisfies such a quantization condition, spin angular momenta satisfies such a condition, and the total angular momenta satisfies such a condition. Okay. Now, if we consider the same thing, the quantization condition for nuclear spin is given by root of I into I plus 1 h cross. Now, the angular momentum vector can take only such orientations such that the projections onto a reference direction are also quantized in units of h cross, and the projections should differ from each other by unity, and the projection values should range from plus I etc. to minus I. ഓക്കെ, അപ്പോൾ ഇങ്ങനെയുള്ള ഡയറക്ഷൻസ് മാത്രമേ നമ്മുടെ ആംഗുലർ മൊമെൻറ്റം വെക്ടറിന് ചൂസ് ചെയ്യാൻ പറ്റുള്ളൂ. ദി ഡയറക്ഷൻസ് that angular momentum vector can take in space are such that the projections onto a reference direction are quantized in units of h cross, and the projections should differ by unity. Okay, അപ്പോൾ എങ്ങനെയാണോ നമ്മൾ ഇലക്ട്രോണിൻ്റെ കേസിൽ ഓർബിറ്റ് മാഗ്നറ്റിക് ക്വാണ്ടം നമ്പേഴ്സ് പറയുന്നത്. അതേപോലെ ഇവിടെ you have mi values which are like this +1 +i etc through 0 if I is integral, and it will not pass through 0 if I is half integral etc to -i. All these are units in all these are quantized in units of h cross. Okay. സ്പേസ് ക്വാണ്ടൈസേഷൻ നമ്മൾ നോക്കിക്കഴിഞ്ഞാൽ ഇപ്പം I equal to 2 ആണെന്ന് വിചാരിക്കാം. When I equal to 2, we saw the magnitude is √6 h cross. And what are the mi values? There are 5 mi values possible: +2, +1, 0, -1 and -2, because it ranges from +i to -i. Okay. Now plotting this. Sorry. So plotting this, this is your reference direction, and the projections along the reference directions have been marked, and only these orientation which gives such a projection is possible. Okay, so if you are to evaluate these angles, it is possible by just finding out the cosine of this angle from this triangle, because you know this length and you know this length. Okay. So these are the 5 different orientations possible in the case of I equal to 2. Now if you consider a half integral value like I equal to 3 by 2, you have 4 different mi values: +3 by 2, +half, -half, -3 by 2, all in units of h cross. So marking the projections like this, these are the 4 different orientations possible for the angular momentum vector. So if you look at how many orientations are possible for a particular I value, for a particular I value, there are 2i plus 1 orientations possible. When I equal to 2, you saw that there were 2 into 2 plus 1, 5 orientations possible. When I equal to 3 by 2, you have 2 into 3 by 2 plus 1, that is 4 orientations are possible. Here it won't pass through 0 because it starts with a half integral value, and when you take values which differ by unity, it will not pass through 0. Okay. I hope this was quite clear to all of you. Thank you.